There we go. Thanks everyone for coming by, and thanks for being patient with the week delay this time. So a bunch of us are in Amsterdam for a conference, so we were pretty distracted last week, so figured moving it off a week was probably prudent. So, but this is a paper that has been long anticipated because CRDTs keep coming up. And so we figured we should probably actually give it a read. Before we dive into it, in detail, would anybody like to give a summary of the paper just to kick off the discussion? That is not myself or Quinn, somebody who's maybe ideally coming into contact with these ideas like more recently.
Happy to give it a go if no one else will. And please correct me because I could well be wrong here. So I think the paper is attempting to outline a sort of, don't know what you would call it, a way of getting something called strong eventual consistency, which is a way for multiple nodes in the distributed system to converge on sort of like an answer for a question, I guess. And it sort of outlines two ways to do that using these things called conflict-free replicated data types. There's op-based and there's state-based, I believe, from memory. And it just talks about what restrictions have to be true for those data types for strong eventual consistency to be possible, basically. Is that fair or not?
Yeah, that sounds great.
Yeah, it's totally accurate. Awesome. Well, does anybody want to give a description of the two types then?
I'll give it a shot without diving into the proofs and trying to pronounce symbols. So the two types are state-based, which relies on convergent data types, where the idea is that you have the data type itself supports merges. And I think that this is the one that's roughly kind of along the lines of like what we think of as like Git merge, or the way that Git handles merges. And the other type is op-based, and it relies on commutativity. So this is kind of like the basic sort of counter idea where it's a commutative operation and it doesn't matter who's changing it. We're relying on commutativity and maybe associativity and idempotence as being sort of like our underlying things that allow us to do the merging, just because we know they're safe as operations. Does that seem like a good description?
Yeah, definitely. Do you have any examples of the second one, maybe?
Counter. So I think that they don't use the terminology here in this paper, but I think they call them G counters, which is a growth counter, where the idea is if you only have an add operation, then it doesn't matter how many times, or it doesn't matter how many different actors are incrementing or like adding. It's always going to grow constantly. So I think that's one example.
Yep, I think vector clock's another example as well.
Can I ask a question? I'm sometimes been wondering how fundamentally different are event-based CRDTs, that is commutative CRDTs, from operational transforms. It seems to me that there is something similar in the two concepts. I know they're not the same, but it's not that clear to me how.
That's a really good question. It's one that I have been asking myself a lot too. The most satisfying answer that I've been able to come up with is that with operational transform, you usually have a centralized server that's responsible for translating the operations into a form that can be shared across all of the different peers. But with the commutative CRDTs, there's no requirement that there's a central server doing that. And the individual nodes are able to do that transformation themselves, both against the operations that they're broadcasting and the ones that they're processing.
Very interesting. I had not seen the central server as a requirement of OT, and maybe that's my misunderstanding of OT. But
yeah,
that's
yeah.
There's a mention in the comparison with previous work of operational transforms. On page 13, page 13, the fourth paragraph. Starts with concurrent editing. Yeah.
I particularly enjoyed the line that that's the one.
Yeah. Yeah. So in most deployments of OT, like Google uses OT, I believe, for, or at least used to, for Google Docs. The model is essentially you have a central server that's collecting all of the events and then translating them into a form that the other nodes would need to update their states to the current version.
So it's, I think I'm seeing it here. The operation in operational transform, the commutativity is an operation. So you have to transform the operation to make it commute. So it's an operation on the commute as opposed to the operations being commutative by design without transformation.
It's also not necessarily that they will commute after being transformed, but you have that like central replica that is defining which order they should be applied in.
But yeah, they do say in that paragraph that was just quoted, thank you for pointing it out, OT algorithms for the decentralized architecture have been proposed, and Oster shows that most of them are incorrect. Mm-hmm. But I think when I read the OT algorithms, I just extrapolated them to decentralized naturally. Mm-hmm. Because there's nothing fundamentally centralized in the design of it. But yes, making the operation transformed itself, like community being an operator, is the difference. Thank you. How could I miss that?
Brian, when you were discussing the two types of CRDTs, I might have misheard you, but you sounded like you were uncertain about whether the op-based ones rely on associativity. And usually the convergent ones are commutative, associative, and idempotent, but then the commutative ones are only commutative, and they instead rely on processing the events according to what's usually called like reliable causal broadcast. So if event B depends on event A, then you're receiving event A before event B.
I wanted to ask about this because this seems like a massive limitation in op-based CRDTs, because like it even says in the paper, there's a line that says something like one that delivers every message to every recipient exactly once. Like, I thought that was mathematically impossible to guarantee exact once delivery. And it's like, if your op-based CRDTs rely on that, like, are they used at all? Like, how can they be? I was a bit unclear on that sort of section.
So they'll often come with like a random number, like a nonce, to make them deduplicated. So you essentially put something in front, like a filter that's like, I've seen one of these before.
Oh, interesting. Right, all right.
Yeah.
And as you can imagine, that can lead to huge memory blowups if everyone's keeping track of every event that they've seen. So a really important aspect for dealing with those sorts of CRDTs is having a garbage collection algorithm that knows when you can remove old events. And one of the ways that's usually done is using this idea of causal stability, where once you know that some event has been processed by everybody and that like every event before that one has also been processed by everybody, you can remove those from your local storage.
How can you know that everybody has processed an event if their, one node happens to be in a partition?
Oh, they talk about this in the just after they like talk about tombstones. They talk about how to GC them, and it's you because you also get updates for the like you're keeping a vector clock, and so because you know the index that the update happened at, and you know the count on the vector clock for every process, as long as all of the clocks have ticked past that index, you can GC the tombstone thing.
But like
Yeah.
what all of this is relying upon is that you know in advance how many participants you have or which participants you have in the CRDT. So like, of course, you can't just garbage collect something if someone new who doesn't have any data will come join the network later.
Yeah,
And
yeah.
it means, sorry, go ahead.
I think they point this out. I think they end up saying the same thing in a different way. That like you can't do any GC if you don't have like, so even if you know that there are 6 nodes, if you're only talking to 5 of them, you can't do any GC because the 6th counter isn't going to tick. So it's
So-
they point out it's not a perfect GC, but like it's better than nothing at least.
You have to be able to assume that either that 6th node will eventually come back online, or that the operators are going to rework the topology to remove it from the network and tell that to all the other nodes.
Ranging a bit off topic here, but I've been approaching this a different way, thinking, yeah, it's a ridiculous memory constraint for everybody to hold all the previous events, but this is easily distributable. So I would tend to keep all the events in a distributed fashion. So everybody is, use something like a DHT. So everybody keeps some of the events, and then have each event list its immediate necessary predecessors. And then you can go ask the DHT for, oh, I missed that predecessor. What is it?
There's a paper that you absolutely need to read. I'm going to find the name of it for you.
Okay, thanks.
2020, Martin Kleppman, Byzantine Eventual Consistency and the Fundamental Limits of Peer-to-Peer Databases. I'm dropping it in Discord.
Thank you.
Everything you just said, absolutely spot on.
Are we maybe building up to that one in this group?
To actually read the paper, we can.
Sorry, what is the Discord? I'm not sure.
Oh.
Maybe I'm not sure I have. I'll
Well,
check.
I have also dropped it in Zoom chat, but we should make sure to get you a Discord link.
Thank you.
I'll tag you in the Discord.
Thanks.
But this paper is basically about what you were just discussing and using content digestible storage to distribute like explicit causal histories for these events across different nodes so that you're able to like really explicitly model the dependencies for different events within the CRDT. And it gives you some very cool properties, including some of the things that you're touching upon here.
Okay, thanks a lot.
I guess another question was like, so we talked about how like storing all history of events is like problematic for the op-based CRDTs, but even for the state-based ones, isn't there a chance that the state can get like quite large if you have like a lot of nodes and stuff? Like, I didn't know, is there a similar garbage collection-y compacting something that you can do for the messages to get passed around if your state grows large, or is it about decomposing, have like many CRDTs or something to kind of try and manage that?
Yeah, state actually usually is more of a problem, surprise, surprise, in the state-based ones. In the naive case, like I believe what they describe in this paper, you're actually passing around huge amounts of states all the time if your data structure is large, and a lot of history as well, right? So you want to garbage collect that too. And so you can start making essentially what Quinn was describing, right? So you make a comparison, hey, is everybody at least up to this point? And then you collect items. It's often a little bit easier to do that because they'll often be based on a stream. And you can say, are we all up to here in the stream? Yes. Rather than saying, how much of this set do you have, right? How much overlap is there?
Makes
And I think
sense.
a really clear example of this is in a CRDT that is usually called OR set, observe to remove set. It isn't given that name in this paper, but it's a state-based CRDT that allows you to add and remove elements to a set. And it's the one they describe that is usually made up of two sets, one representing the elements that were added, one representing the elements that were removed. And the issue here is that you can have a set with no elements in it that has millions of tombstones if everything has been deleted. But when you do the sorted garbage collection algorithm, if you know everyone is synchronized to some point, you can compact all of those together and remove the tombstones that are no longer relevant.
It's interesting. I guess the other implication as well is that, like, presumably state-based CRDTs end up with a much chattier network because you have to send the state to every node, as far as I understand. Whereas I don't know if that's true for the op-based ones, right? Like,
they specifically call this out, or I guess they sort of implicitly call this out when they're talking about in their example at the end with the web crawler where they're like building a DAG and updating it. They specifically say, like, we don't do a state-based CRDT construction here. We use an op-based one because otherwise we need to send all of the state every update, which is a lot.
I mean, you could technically do something like, well, you send the state to some peer and rely on that peer then relaying the state further with like your changes included. Because they, well, if they send their state with their updates to someone else, it inevitably contains your updates, right? So you could somewhat rely on that and reduce bandwidth usage by that, maybe.
But how do you know that everyone's connected, well connected?
And what if the state is really huge? I mean, it's just a kind of a bandwidth optimization to rely on updates most of the time on deltas. And then maybe occasionally when you're out of sync, try to ask for a snapshot as a way to.
There's actually an extension to, sorry, go ahead.
I think we're going to say the same thing. You go.
There's actually an extension to state-based CRDTs called delta state-based CRDTs.
Right, yeah, that makes sense.
Are essentially doing that. They are more difficult to reason about because you often end up needing some more bookkeeping processes that run in the background. You might sometimes see them called like anti-entropy algorithms, but harder to think about, but more efficient because you're just passing around these deltas.
I think you could technically also do this thing where instead of sending over your current state, you start some protocol that interactively figures out what the delta is. I'm not sure whether that's delta state-based CRDTs are. Are delta state-based CRDTs where you essentially know what state other replicas are in? So you, in advance, before sending, you know what to send?
You're sending diffs around.
Yeah, but diff based on what? On the previous pre-operation state or on what you expect your proxy, your vis-a-vis to have? That was Philip's question. It's a good one.
Yeah,
but I would think certainly based on previous pre-operation state.
Yeah.
But then how is the pre-operation state not the delta? Maybe sometimes the operation is complex, creates a lot of changes, and it makes sense to, instead of sending the operation, sending the delta. But it feels weird to me that you can just send the operation.
Just sending the operation, there's often, because you can build op out of state and state out of op. And so there's sometimes this like mixing, which makes it confusing of like, I'm going to get exact once calls a broadcast by putting in a state-based CRDT and sending that across. And then inside of that, there's an op-based function that will then run, right? But yeah, the deltas, I believe it's literally just the like the update delta going across without prior knowledge. It's been a while since I've read that paper, but.
Okay, so the delta to the last state you sent, so you keep a record of which state you send to other peers. And so you send the difference between the last time you sent them something and your current state.
So you'll often have a vector clock for everybody else. So this is assuming that you have a finite number of peers. And you essentially say, I know Philip is at tick 6, or like Philip 6, and Brooke 2, and James 7. And then I have some line of like, okay, well, this is the last time I saw something from James, this was his clock. So I know that he's roughly here, and this should be the delta that I just sent him. That can end up with a lot of state when there's a lot of peers and a lot of updates. So there's a bunch of improvements on that too, like dotted version vectors and like other things, just to make that faster and smaller. But you end up, as Quinn was saying, having to hold on to a bunch more state about the network then, right?
It ends up being trading the size of your state for the size of your metadata about that state.
Yeah, I guess so. Something else you could do would be like starting an interactive protocol with someone else, where during that protocol, you figure out what the difference is between you and your peer. But that means more latency, like network latency, because you're doing this interaction.
What I think I would tend to do in that case is just keep my own idea of snapshots. Like I take, let's say, a snapshot every 100 events on my clock. And it doesn't matter if somebody else has another clock. And if they're not synchronized, then they can say, okay, well, what I give up, what's your latest snapshot? And the delta's from there. And then you don't have to know what they knew. You're just saying, well, my last snapshot was at my tick, whatever, and take it from there. And I just record the events from then.
Which is kind of like an interactive protocol, if I understand you correctly, right? Where the other person is communicating to you what they're,
but
what they know about, right?
They not even. They're saying, you know, I'm interested in the latest. What do you have? And you say, well, my latest was at tick whatever plus deltas. Now, of course, it's my tick, so they have to understand my tick. But the advantage is, I think you wouldn't need to know how many peers you have in that case. You just know, hey, on whatever clock these people have for themselves, that's what they have. I'll get this, and I'll be up to date with them, no matter what the network thinks. And then when I get something from someone else, well, I can compare, oh, it's relative. Yeah, I'm not sure how to handle relative clocks then, honestly.
You will really like the Martin Kleppman paper that I'll post it.
Really looking forward to it. So when were we doing it?
One of the complications with your proposal is that in the presence of network partitions, you can end up with cases where different nodes are going to go down entirely divergent histories. And so if you throw away that metadata about how they got to those histories, you can't just naively compare them together because you might end up throwing away events.
Yep. Which is why we wanted to keep all the events. And then find the kind of branch point, earlier branch point.
But if you can assume that you are, like if there's a total ordering between your state and the node that you're syncing with, what you're describing works. One of the benefits of these CRDTs, though, is that they allow you to merge data over partial orderings, where I can't like strictly say I'm ahead of you or you're ahead of me. We might be ahead of each other in different ways.
Yeah. I'm not assuming total ordering. You're absolutely right there. And that and there it makes sense that I could get your sequence and then say, well, I've got all these events you didn't know about, and let me apply those. And tell you back, hey, I knew about this stuff you didn't.
Who's going to say join semi-lattice first?
Who's itching for that?
Seems you are.
Quinn, do you want to expand on the partial ordering stuff?
Yeah. I'm not going to say the word monad, but I am going to say the word semi-lattice. A semi-lattice, for those of you who don't know, is a algebraic structure in abstract algebra that basically describes objects within some set that have either a join or a meet operation against them, which is basically responsible for taking two elements of that set and combining them together. But it does so in such a way that the combination of those elements is going to be what's called the least upper bound for those elements. So what that means is that it's going to be there's a partial ordering of these elements, and the least upper bound is the least element that is greater than both of those elements. So the intuition here is that when you're merging these different elements together, you're always going to get some element that is moving further and further in one direction. And I guess I never explained what a partial order is, but a partial order is when you have an ordering over elements where you can't necessarily compare all of the elements together directly. And a good example of this would be like straight
Number
addresses, for
clocks.
example. If I say that I live at like 2 Front Street and someone else lives at 3 Front Street, I could say that my address is less than theirs because the number is less and we live on the same street. But I can't compare like 7 Front Street with 8 Jerry Street. There's no way to order, at least there's no intuitive way to order the names of the streets there. So we have a partial ordering. And semilattices basically join and meet semilattices really give you this elegant way of merging elements within a partial ordering such that there's always a guaranteed way to get a consistent value that is going to be greater than the 2 elements that you're merging. And it does this in a way that's commutative and associative and idempotent, which means that if you're using the semilattices as the basis for CRDTs, and you can prove that what you have is actually a semilattice, then more or less for free, you are also guaranteed to have a CRDT. That was kind of off the cuff. Did that make sense? Does anyone have any questions about that? Yeah, Ryan?
What's meant by greater than here? Like, could you make a more concrete example of that? And does that kind of imply like an add bias to the way that the CRDTs work?
Yeah, good question. So no to your second question, but I'm going to come back to it in a second. And by greater than, let's see a good example. I feel like someone mentioned vector clocks a moment ago, but if you have 2 vector clocks, let's say it's a vector clock with 2 elements in it. You have 1, 1 and 2, 1. In that case, it's easy to see that the second vector clock is greater than the first one because they only differ in one component, and the second one's value in that component is greater. But if you had 1, 2 and 2, 1, then there's no obvious ordering between them. The first one is greater in one way, and the second one is greater than the other in another way. But with the semilattice, the join operation might turn that into I forget if it's 2, 2 or 3, 3, but you end up with something that is greater than both of them. Yeah, just allows you to construct this order across all the events in the system, even though they may not be directly comparable.
Right, so the system is progressing either which way.
Yeah, exactly.
Okay. And about the add bias, you had to add something else.
Oh, yeah, right. So CRDTs do often have some sort of bias associated with them, and except it doesn't. Where am I going with this? So, okay, yeah. So if you have two states that are in conflict with each other, and you need to choose that like greater least bound for them, there might be more than one way to do that. And I think the most obvious example of this is if you're dealing with a CRDT for a register. So if you have some register that you can write values to, and you can overwrite them, then you might end up in a situation, and you can also, let's say, delete values from them. You might end up in a situation where I add a value, I send that to you, then you delete that value, and then I set it to something else. When we synchronize again, you've deleted that same slot, and I've changed its value. Which one of us should win? And usually there's not a good mathematical answer to this question, and it really comes down to thinking about what this data represents within the context of the application that it's being used in. And so you put a lot of thought into coming up with what are sometimes called intention-preserving CRDTs. So in most, but not all cases, that means that you want to have a bias towards writes over deletes, for example. And in many cases, you can almost think of a write as being like a delete of the original value and then a write of the new value. So in a sense, it kind of subsumes the deletion, but that's also not always the correct approach. And for example, if you're making like an admin panel for a website where moderators can delete problematic content, in that case, you would probably want their deletes to override more rights to that content. So it always comes down to thinking about the application that you're building and where the data fits into it.
Martin Kleppman has a great quote about how writing CRDTs is really easy, but making them intention preserving and fast is really hard.
Mm-hmm. There's actually, sorry, go ahead.
I was just going to say there's a really good blog post, 2 blog posts on this idea, that where it starts with explaining what a join semilattice is and then steps into like how that's used in like a CRDT. I'll post it in the Zoom chat here. It's not in the Discord either. But
I love semilattices.
Yeah, he does an example using cities and doing located in and yeah, but it's just really good. I thought it'd be worth sharing.
Nice. So I've been spending a lot of time looking at Datalog lately, and there's a experimental implementation of Datalog that recently came out called Ascent that adds lattice-based types to the language. And this ties into your question, Brian, because lattices are kind of a more complete structure than semilattices, where semilattices move in one direction, lattices can also move in the other. And so the way this language works is you essentially have these types that are semilattices, but then you can also take the dual of that semilattice to end up with a type that moves in the other direction. And that's one of the ways that you can model this sort of bias that you're talking about. If you want to be biased towards larger numbers, you use the integers semilattice. But then if you want to be biased towards smaller numbers, you use the dual of the integer semilattice, for example.
So this is
kind of they try. Oh, sorry, go on.
Oh, this is kind of the idea of like with if you have like a counter, but you want to not just add but subtract, so you keep 2 separate. Yeah.
Mm-hmm. That's what I was going to say. Yeah, is that what they do in the paper when they have the 2 that they kind of combine to allow for additions and subtractions? But yeah,
it's not. So the full lattice. Sorry, you're going to explain it to you. Go for it.
Oh, I was going to say in the paper they're not directly thinking about things in terms of like combinations of duals of semilattices like this, but I think that that's a really insightful connection to draw, and that many of these more complex CRDTs that you build up are made up of the composition of simpler CRDTs and kind of their inverses or duals in a way that kind of matches up with that intuition.
So it's the first thing when I read about them or whatever, I was like, oh, that's amazing if I want to grow only counter. But like, how do I model like actual problems in this, right? And obviously like subtractions, a trivial example of that. And I still think that is, what Kleppman's talking about is still a challenge to try and model your problem in terms of like CRDTs and join semilattice or whatever. But I guess that's to help with that problem. It's tricky.
So the pattern where you add a decrement counter or the set of removed objects or whatever is shows up in the paper. Are there other techniques, patterns to do the same things that aren't just like keep a copy of the nega world?
There is, and I would like to explain them, but it looked like Brooklyn had something on her mind when I interrupted her.
Oh.
I was just going to go back really quickly and clarify on lattices. So a semilattice says that any 2 items, or joint semilattice says any 2 items will have a shared descendant, right? And join says the opposite, that they'll have a shared parent, right? A full lattice says they have both. So it's a much, much, much more rigid structure, which is why you're able to walk up or walk down it. But there's way fewer of them, like vanishing small number of them. And what we want from a CRDT is this large number of states that are all valid. So if we combine them like this, or we combine them like that, it's totally fine. If you try to do that in a lattice, there's only typically one way to do it, right? And that loses the practical properties that we want. Anyway, sorry, back to Quinn.
Yeah, just to clarify, NA, was your question about whether there are other ways of composing CRDTs that are not just combining like the positive and the negative version?
It was more that, I mean, I guess yes, technically, But mostly I was curious if there were like, I guess, actually, yes. Yeah, I guess that's a good summary of it.
Okay,
The-
cool. Go ahead.
I put in the Zoom this INRIA article quotes another INRIA article which goes in more detail about kind of known useful compositions. It's a kind of list of a few well-known CRDTs. It's worth going. It's a little catalog. It's quite old, so I'm sure there's much more now, but it's a good starting point. I found it a good starting point.
Oh yeah, this one goes deep. And actually, it mentions the one that I was going to talk about. Page 35, RGA, replicated growable array. And one of the places where this composition ends up being really important is when you're dealing with sequences and lists of elements. And one way of doing that is using this op-based CRDT called replicated growable array. It's essentially a CRDT array where you represent insertions as being the elements that you're inserted rooted to like the point in the array where they are being inserted. So you end up with these different branches representing the different like blocks that have been added to the array. But where this gets really interesting is that when you have a CRDT like this, that's essentially acting as a container for elements, there's no reason that you can't compose that with another CRDT and have a CRDT that contains CRDTs. So then, for example, if you have an RGA that contains G counters, then that's a CRDT of growable counters. And you can insert into it and increment them and so on in a way that is going to converge. And then when you combine this with other types of sequences, ones that allow you to like rearrange elements, for example, there's, especially in the past couple of years, been some really interesting work on modeling like JSON arrays and lists and so on using CRDTs. You can end up with these cases where you are essentially building up like lists of elements that can be reordered, where those elements can themselves be CRDTs and can, for example, be CRDTs representing like JSON objects, which can themselves have keys mapped to CRDTs representing JSON numbers or JSON lists and so on. And you basically end up being able to build up arbitrary schemas and application states and so on just through the composition of CRDTs for primitives like numbers and lists and objects and such. It's very much a cutting edge part of the field, and there's a lot of research being done to find the most efficient ways of doing this. But there's some very cool stuff happening in this space.
Yeah.
So we need to work on a language name. Sorry, I was just going to say we need to work on a language name for the first CRDT language.
Maybe this answers your question, Na, but I was thinking, like you were saying, do you always, for example, you have this set of elements and you can remove stuff from it. The obvious construction for that is like you have two grow sets. One is for the positive stuff and one is for the negative stuff, right? Another construction for it would be, and I bet this is somewhere described, you have a grow set of all of the elements that are inserted, and you have a vector clock, which keeps like essentially some kind of revision around. And if you delete an element, you just remove it from the set and increment the clock on your end. And so if someone else compares their CRDT state, what they first do is they look at the clock. And if they figure out that there's like, they're just strictly ahead, but like the grow set is smaller, then they just take the grow set, the smaller one, even though, yeah. Well, it's not a grow set then anymore, but yeah, I hope that gets the point across.
Yeah. If you want to add back the element, then maybe you want to record when it was deleted on the clock and make that part of the element. It's not, yes, there's catalogs, but there's still a lot of thinking around making this work well. It's not yet, we're still working on that design pattern catalog, let's put it this way.
That makes sense, yeah. And it's also, I think that's the answer to the question I actually wanted to ask, which are like, what are the the CRDT atoms, the smallest elements or whatever that compose? And the answer is, we don't know yet. We're still working on it.
Yeah, it's more like a set of principles, like literally mathematical principles, where you could come up with an infinite number of CRDTs. There's a certain number of them that are known, and we keep finding more. In terms of being able to compose them together, there's a bunch of ways of doing that. But as Quinn mentioned, right, this is very, very early field. Like this paper that we're reading now is from 2011, right? And it describes techniques that are older as well, and kind of creates a single idea for them, right? But that's 11 years ago, right? This stuff's all super, super new. Putting them in production has, it's like, oh, wow, state gets really big really fast. We have to learn, figure out all these pruning techniques. So it's like very, very early days. The compositional part, I think, gets lots of people really excited because it's like, well, we know how to take simpler things and stick them together. But now you have all kinds of challenges around intention preservation. So, Quinn described this system where you have a pointer, but that pointer is just an element in this data structure. So if you delete that, well, you might still be updating the rest of the data structure and not know it, right? So like there's some other ways of trying to manage doing composed states. And so one of the main problems with adoption is that they don't compose really nicely yet, right? So we're still figuring out like the basics.
I forget the name of
That
the
makes
paper,
sense.
but Martin Klotman had another fairly recent paper where his team did a survey of a ton of the existing implementations of list CRDTs and found that almost all of them had some sort of intention violating bug, where you might end up with cases where moving an element would result in some nodes ending up with 2 of that element, or deleting it may only delete it if it wasn't moved on another node and things like that. And he proposed a generic way of resolving this problem by combining like a register as a pointer with a list CRDT and something else, but I forget the details and also the name of the paper. There's actually, he maintains a website, crdt.tech, that has a list of all of the CRDT papers. And if you want a fun week, just read all of them.
I think, Adam, you mentioned earlier a programming language for CRDTs. I don't know if this is still an active project, but there's this language called LASP that I'll put in.
I think I've heard of that. Yeah.
I just put in a link for the paper, which is Christopher Mickeljohn was working on it, which what was the author of one of our previous papers in this group last week, or last time.
Is it trying to set like CRDTs as like first class objects or something in the language or something? Or
I haven't read the paper, just heard of it.
Yeah, and it was part of a larger project. Sorry, go ahead.
Oh,
it was
I
part
was
of
just
a
gonna say,
larger...
delay, you go.
Okay. It was part of a larger project of his called Partisan, where he was trying to make an alternative Erlang runtime or distribution runtime, and that was going to involve first class support for CRDTs so that you can really easily synchronize objects between Erlang nodes.
Yeah, so there's sort of an ongoing question in programming language circles about whether your data should even be part of the language. Are databases also languages, right? Or the query languages, all of this stuff. And there's massive, as Quinn and I have been discovering, there's massive overlap between these fields. And most of this has been happening in the database world, right? Because we're literally talking about moving state around. But where is the, there's the famous impedance mismatch between databases and the rest of the language. But there's been a number of attempts to unify that and say, well, maybe they don't have to be completely separate. And getting those into more mainstream languages is hard because people want to mostly do work on things locally, and they're not doing mostly synchronization. CRDTs have an overhead they're getting faster, right? But they're known to be slow and use up a lot more space. So you pay a cost for them. But if you're doing lots of distributed stuff, they're a very simple model in that you don't have to maintain this huge mechanism and consensus and all of this stuff to share state eventually.
On the note of CRDT languages, there's also a really exciting project. I don't believe it's in active development anymore, but it was out of Berkeley around 2014, 2015 or so. The larger project was called Boom, but they developed a language called Bloom as part of that, which was a language for building distributed systems using semi-lattices. And basically the way it would work is all of your types were these semi-lattices. They weren't actually using the word CRDT, which I find interesting, but something that I think both Brooke and I have noticed in doing a lot of this research is that people who talk about semi-lattices and people who talk about CRDTs don't necessarily talk to each other, even though they're talking about the same thing. And so in this Bloom language, you're structuring your application state in terms of these like built-in semi-lattice types that are essentially CRDTs. But the interpretation of those types happens on the individual nodes and basically happens at read time. And then what's really cool here is that the language does static analysis to look at how the application state is being used and manipulated and transformed to find the points in your logic where you are doing what's called non-monotonic logic, places where you are not manipulating that data in accordance to the requirements of a semi-lattice. And then that really explicitly brings those areas to your attention so that you can either change your program logic to make it compatible with something like a CRDT. You can introduce a coordination protocol to more interactively talk to another node and reach consensus about something. Or you can just choose to accept that inconsistency as unavoidable and okay. And that's a really interesting approach to distributed systems that I haven't seen many people take, because I think a lot of systems are still targeting strong consistency as the end goal and ignoring the reality that the world is far more complex than we can ever imagine.
And good news, next month, we're reading a paper from, I don't know if it's actually part of that same program, Boom, but it's a lot of the same people involved.
I believe it is.
Yeah, so keeping calm when distributed consistency is easy. So
yeah, they mentioned calm, like they're all capitalized on the Bloom homepage as well, so it must be related.
Yeah, yes.
We did diverge for the paper quite a bit. Sorry about the hijack.
It's all good, right? We'll see where the conversation takes us every time.
Oh, I had a question about understanding, because I did not entirely grok all of the things going on here, especially the formalization of up-based CRDTs. What is the point, significance, reason for the prepare update and the effect update distinction separation? Like I saw how they used it in the example where they're using it for like precondition checks and like generating unique IDs for stuff or whatever, but it didn't seem super clear in the formalization why that was like important or necessary.
Yeah, I'm not a huge fan of the treatment of op-based CRDTs in this paper specifically. I found that description confusing for the same way. They're not usually described in terms of these prepare and update operations, at least that I've seen elsewhere. And I think the best comparison I can think of is to view it through the lens of operational transform and think of the like prepare and operations as being that equivalent of what the centralized server is doing in operational transform, except distributed across all of the different nodes. I don't think they do a great job of motivating the distinction in this paper, though. I don't know if anyone else has a better intuition about this, but I found that confusing too.
I can't remember the prepare one at all, but the effect is what we normally think of as actually applying the operation, right? And then I believe it also then in their construction, did they then also pass it around after that?
Yeah, yeah. So they like split the update into the prepare and the update, and then package it in this tuple, and then maybe send it. But it also sounded a lot like all of this is happening. A lot of it is local, and so it was just sort of confusing.
Yeah. Mm-hmm.
Yeah, if I remember, again, it's been a while since I've dug through this like in detail. But if I remember correctly, it's essentially looking at it being like, do I already have this? Do I need to apply it at all? Yes, no. Actually apply it and then tell your friends, right? Tell the other nodes.
Mm-hmm.
Yeah, like I can't actually remember firmly off the top of my head. So
my intuition would be prepare the kind of package because it's only at the source. So you kind of package the event so that it's easily consumed by the replicas.
Mm-hmm. There's another list CRDT called Yada, which I think is the closest thing I've seen in the real world to this prepare update construction. And Yada is a list construction that basically represents different blocks of the list or the array. And all of them are denoted by the index of the left side of the block and the right side of the block. So in using those indices, you're able to order all of the blocks with respect to each other in a consistent way. But where Yada gets a little bit confusing is that the indices may actually be different across all of the nodes. So nodes have their own local model of the list. They apply operations to it, but then before they send those operations to the other nodes, they actually transform them to have different indices that are going to be universally applicable to other nodes after those nodes apply their own transformations to translate them into their own local model of the world. And I feel like that probably maps to the prepare idea here, but it's not actually something I've seen explicitly called out anywhere except for this paper.
Okay, that makes a lot more sense, and it makes me feel better about not quite grokking it. Sorry, go ahead.
Sorry, no, I was thinking loud. I thought it was actually on mute. I wondered if the prepare update was around like causally, or like what we mentioned before earlier when I said like exact once delivery isn't like, is that what that is? I think that prepare update bit.
Yeah, well, so because they commute, right? It shouldn't matter the order that we get them in, just that we only get them once, right?
Right. Yeah.
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 Yeah, actually, I think that's right here.
These ones are not necessarily associative though, so you still need to, you can apply them in any order as long as you do so according to their dependencies.
So you should be able to get the event in any order, but if it comes around, for example, like with a vector clock, then yeah, you've got to go and linearize it and then play over them, right?
There was definitely reading through this, especially the dense mathy section. I couldn't help but think that it would be a lot easier to grok quickly, better. I don't know if they had something like a little interactive diagram on the side or whatever that you could play with. There's I forget what they're called, but like a Nicky Case style thing. Explorables, that's what they're called.
Braid, which is they're the W3C. They're trying to do distributed update semantics standardized instead of HTTP. One of their CRDT algorithms has a nice little interactive thing on that shows how the state is moving around on their site. Sounds like, I don't think it's actually interactive, but it's animated at least, which sounds similar and gives a nice intuition.
Yeah, definitely. That sounds great.
This is very off topic, but Martin Pletman, who we've mentioned a couple of times, works at a research lab named Engine Switch, and they recently released a tool for tablets for creating like live dynamic models that give you like these really cool like interactive visualizations of dynamic systems. And it'd be very cool to see some of that applied to CRDTs, but I recommend looking that up if you are curious, because it's a very cool piece of software. I don't remember the
Given how
name
much-
off the top of my head, but so good.
Sorry, I think it's the delay again. Given how often Martin's come up in this call, we should have just invited him.
Yeah. His papers are great.
All right, awesome. Well, actually, that is the hour. So I'm going to stop the video, or I guess I'll give anybody a chance to put any last thoughts on video. Stop the video, and then we can hang out for a little bit more for the after party, as per usual. Any last thoughts?